Did you know that the average soldier's chance of surviving a battlefield injury in World War I was terrifyingly low? But just 2 decades later, that number changed dramatically. Why? What happened in that short span of time that transformed medicine forever? The answer is found in the crucible of another global conflict, a period of immense pressure that forced innovation at an unbelievable speed. How do you treat millions of people for infections when you don't have a reliable cure? How do you keep a nation from starving when food is scarce? How do you repair a face that has been burned away? The problems were huge. The solutions that emerged were nothing short of revolutionary. They came from strange places: a forgotten piece of mold on a lab dish, a deadly chemical weapon, the simple act of sorting wounded people. These discoveries were not just about winning a war, they were about survival, and they laid the foundation for the medicine we rely on today. Number 15, when does a hospital begin on the battlefield? The idea of emergency medical care seems so normal now. Someone gets hurt, you call an ambulance, and trained professionals arrive. They start treatment right there on the spot. But this system, this idea of bringing the hospital to the patient, had to be born out of necessity. Before the 1940s, medical care was something you got at a fixed location. You had to get the patient to the doctor, not the other way around. The battlefield was a place of chaos. The best a wounded soldier could hope for was a stretcher bearer, someone to carry them away from the danger. The journey to an aid station could take hours, even days. Many died along the way from blood loss, shock, or infection. The problem was time. Every second a person bled, every minute their body was in shock, their chances of survival plummeted. The military leaders and doctors during the Second World War understood this brutal math. They needed a new way. The solution was to create a new kind of soldier, someone who was a fighter but also a healer. This was the birth of the combat medic, or the naval corpsman. These were not just people with a few bandages. They received extensive training. They learned how to control severe bleeding with tourniquets and pressure dressings. They learned how to administer morphine to manage pain, a critical step in preventing shock. Perhaps most importantly, they carried blood plasma. This dried blood product could be mixed with sterile water and given intravenously right there in a ditch or a foxhole. This was revolutionary. It meant you could start replacing lost fluid volume long before a patient ever saw a surgeon. You were fighting shock, the silent killer, at the point of injury. This was a fundamental shift in medical thinking. The golden hour, the idea that a trauma patient's best chance of survival is within the first 60 minutes after injury, was being learned the hard way. The medics were the first link in a new chain of survival. This chain was called the chain of evacuation. It was a system designed to get a soldier from injury to definitive surgery as fast and as safely as possible. It started with the medic providing immediate care. Then the soldier would be moved to a battalion aid station, a small mobile unit just behind the front lines. Here, a doctor could perform minor procedures and further stabilize the patient. From there, they might go to a clearing station and then a field hospital and eventually a general hospital far from the fighting. Each step was designed for a specific level of care. It was an assembly line for saving lives. The work of these medics was documented in countless reports and memoirs. One of the most influential figures in conceptualizing this system was Major General Paul Hawley, the chief surgeon of the European Theater of Operations for the U.S. Army. He relentlessly pushed for better training, more resources, and a faster evacuation process. His reports, like the one titled Medical Service in the European Theater of Operations, detailed the successes and failures, providing a blueprint for future military and civilian emergency medical services. The numbers tell the story. In World War I, the mortality rate for American soldiers who were wounded in action was about 8.5%. In World War II, it dropped to around 4.5%. A huge part of that improvement was due to faster, better care at the front. This concept didn't stay on the battlefield. After the war, doctors who had served as medics and surgeons came home with a new understanding of trauma care. They saw the chaos of car accidents and industrial injuries and realized the same principles applied. The idea of a trained first responder was born. The development of modern ambulance services and paramedics in the 1960s and 70s can be traced directly back to the lessons learned by combat medics. A landmark 1966 report from the National Academy of Sciences, Accidental Death and Disability, The neglected disease of modern society highlighted the terrible state of civilian emergency care and used the military system as a model for what could be achieved. Today, when a paramedic starts an IV on the side of the road, they are using a technique and a philosophy that was perfected under the most extreme conditions imaginable. What do we still not understand about emergency care at the point of injury? If we can give plasma on the battlefield, why can't we perform more complex, life-saving surgeries in a mobile setting? What is the absolute limit of medical intervention that can be done outside a hospital? And as technology advances, could remote-controlled drones or robots one day deliver trauma care in places too dangerous for a human medic to go? Number 14, who decides who lives and who dies? It's a terrible question. Imagine a place with 100 injured people and only enough doctors and supplies to treat 10 of them properly. Who do you choose? The person screaming the loudest? The one with the most horrific-looking injury? The one who is quietest? This is not a theoretical problem. It's a reality in any mass casualty event, from a natural disaster to a battlefield. The system we use to solve this impossible puzzle is called triage. The word comes from the French verb trier, which means to sort or to select. And while the concept has been around since the time of Napoleon's armies, it was during the Second World War that it was refined into a science and implemented on an unprecedented scale. The old way of doing things was simple. First come, first served. Or, even worse, the highest ranking officer got treated first. This was horribly inefficient. A soldier with a minor shrapnel wound might be treated before someone with a severe internal injury who was just a few minutes from death. You would waste precious time and resources on those who would survive anyway, or on those who had no chance of survival, while a person who could have been saved was left to die. The military medical corps realized they had to change their thinking. They had to focus on the goal to save the most lives and return the most soldiers to duty. This meant making cold, hard calculations. They developed a classification system. It was simple, so it could be used quickly in a high-stress environment. The wounded were sorted into categories. The first group was the minimal cases. These were the walking wounded. They had cuts, bruises, or minor fractures. They could be treated quickly and often sent back to their units. The second group was the immediate cases. These were the soldiers who were critically injured but had a good chance of survival if they received immediate surgery. Think of people with severe bleeding, chest wounds, or blocked airways. They were the top priority. The third group was the delayed category. These were soldiers with serious injuries that required surgery, but their condition was stable enough that they could wait. This could be someone with a major bone fracture, but no immediate threat to their life. The final, and most difficult, category was the expectant group. These were soldiers with catastrophic injuries, such as massive head trauma or severe damage to multiple vital organs. They were deemed unlikely to survive, regardless of the care they received. They were not abandoned, but they were given pain medication and comfort care, while the limited surgical resources were used on those in the immediate category. This was a brutal but effective system. It was championed by surgeons who saw the reality on the ground. They knew that by focusing on the immediate group, they could save people who would have otherwise died waiting. It required a new kind of discipline from doctors and nurses. They had to resist the natural human urge to help the person who looked the worst and instead follow the logical system. It was emotionally taxing, but it worked. The implementation of triage in aid stations and field hospitals dramatically increased the efficiency of military medicine. More people were treated and survival rates improved. This system allowed a small medical team to manage a huge influx of casualties, something that happened regularly. The principles of triage were so effective that they were quickly adopted by civilian medicine after the war. Every modern emergency room uses a form of triage. When you go to the ER with a sprained ankle, the nurse who first sees you is performing triage. They assess your condition and determine that you can wait, while the person who just came in with chest pain needs to be seen immediately. Paramedics at the scene of a multi-car pileup use triage tags, often color-coded, to sort patients into the same categories developed decades ago. It's a direct legacy. The work done to formalize this process was immense. Military medical journals from the period, like the Bulletin of the U.S. Army Medical Department, were filled with articles and reports on the best practices for sorting and managing casualties. They studied transport times, surgical outcomes, and staffing levels, all to refine the system. But what are the ethical lines we still haven't figured out? In an age of advanced technology, should someone's age or pre-existing health conditions factor into triage decisions? How do you apply these principles in a situation like a pandemic where the resource being rationed isn't a surgeon but a ventilator or a hospital bed? And can an algorithm or artificial intelligence ever make these life or death decisions better and more ethically than a human? Number 13, how do you rebuild a human body? Losing a limb is a profound trauma. It changes everything about a person's life, from their ability to walk to their sense of self. For centuries, the answer to this loss was a simple, often crude prosthesis, a wooden leg or a metal hook. These were functional to a degree, but they were heavy, uncomfortable, and limited. They were replacements, but they didn't come close to restoring what was lost. The sheer number of amputations during the, Second World War created an urgent need for something better. Hundreds of thousands of young, otherwise healthy people needed to be able to return to a productive life. This demand fueled a revolution in the fields of prosthetics and rehabilitation medicine. The problem with old prosthetics was the materials. Wood and steel were strong, but they were not well suited to the human body. They didn't flex. They were hard to shape precisely. The connection point, the socket where the patient's residual limb fits into the prosthesis, was often a source of constant pain and skin breakdown. The war accelerated the development and use of new materials. Plastics and lightweight alloys, like aluminum, which had been developed for the aviation industry, started to be used in prosthetics. These materials were a game changer. They were lighter, stronger, and could be molded to create a much more comfortable and customized fit. A government-sponsored research program in the United States, the Committee on Artificial Limbs, was established in 1945 to coordinate efforts between surgeons, engineers, and scientists. This was a new interdisciplinary approach to the problem. Engineers began to study human movement, a field called biomechanics, in a much more systematic way. They analyzed the mechanics of walking and gripping to design prosthetics that could mimic natural motion more closely. They developed new knee joints that were more stable and allowed for a more natural gait. They created hands that could be opened and closed using a harness system controlled by the user's shoulder movements. These were still mechanical devices, a long way from the myoelectric arms of today, but they were a huge leap forward. They gave amputees a level of function and independence they had never had before. For example, the so-called split hook hand, while looking simple, was an incredibly versatile tool that allowed users to do everything from buttoning a shirt to using a hammer. But a better prosthesis was only half the battle. The other half was teaching people how to use it and how to adapt to their new reality. This led to the formalization of rehabilitation medicine as a distinct specialty. Dr. Howard A. Rusk is often called the father of this field. During the war, he established a rehabilitation center for the Army Air Forces. He rejected the old idea that once a patient was medically stable, the doctor's job was done. He argued that medicine had a responsibility to treat the whole person, to help them regain not just their physical health, but their place in society. This was a radical idea. His centers combined physical therapy, occupational therapy, and psychological counseling. Therapists would work with amputees for months, teaching them how to walk on their new legs, how to use their prosthetic hands, and how to overcome the emotional challenges of their injuries. They focused on ability, not disability. The goal was to get these individuals back to work, back to their families, and back to a fulfilling life. The success of these military rehabilitation programs was undeniable. After the war, Dr. Rusk went on to found the Rusk Institute of Rehabilitation Medicine in New York City, which became a model for similar centers around the world. The Veterans Administration also played a huge role providing lifelong care and prosthetics for amputees and funding a great deal of research and development in the field. The knowledge gained wasn't just for soldiers. It was applied to civilians who had lost limbs in accidents or due to diseases like diabetes. The whole person approach to recovery, which is now standard practice in treating stroke, spinal cord injury, and a host of other conditions, has its roots in these wartime efforts to rebuild broken bodies. What are the ultimate limits of prosthetic technology? Will we ever be able to create a prosthetic that provides a true sense of touch? Can the brain ever be connected so seamlessly to an artificial limb that it feels like a natural part of the body? And what are the philosophical questions we will face when prosthetic enhancements begin to offer capabilities that surpass those of a natural limb? Number 12, can you make surgery bearable in a war zone? Surgery is an act of controlled violence. To heal the body, you must first cut into it. For that to be possible, you need anesthesia. You need a way to render the patient unconscious, to block their pain, and to keep them still. In a clean, modern hospital, this is a highly controlled process with sophisticated machines and a wide array of drugs. But what about in a field hospital, a tent filled with dirt, and the sounds of distant battle? What about on the deck of a rolling ship? The challenges of providing anesthesia in a forward military setting during the 1940s were immense. The equipment had to be portable, simple, and reliable. The drugs had to be fast-acting and safe, even in the hands of a nurse anesthetist who might be working under extreme pressure with limited support. For decades, the mainstays of anesthesia had been ether and chloroform. They were administered using a drip method, where the liquid anesthetic was dripped onto a mask held over the patient's face. This worked, but it had problems. Ether is highly flammable, a huge risk in an environment where sparks were common. Both drugs could be difficult to control, and patients often had long and unpleasant recovery periods with severe nausea and vomiting. In a crowded ward with limited nursing staff, this was a major problem. The military needed better, safer, and more efficient options. One of the most important advances was the widespread adoption of intravenous anesthesia. A drug called sodium pentothal had been developed in the 1930s, but the war was its proving ground. It was a barbiturate that could be injected directly into a vein, putting a patient to sleep in a matter of seconds. This was a massive advantage. It was quick, the induction was smooth and pleasant for the patient, and it wasn't flammable. A small kit with a syringe, some needles, and ampules of the drug was incredibly portable. It could be used to put a patient to sleep quickly before a more prolonged anesthetic like ether was started. It was also used as the sole anesthetic for short, painful procedures like changing a burn dressing or setting a broken bone. The speed and simplicity of pentothal saved countless hours of operating time and made the whole surgical process much more efficient. Another key innovation was in regional anesthesia. Instead of putting the whole patient to sleep, a regional block numbs only the part of the body being operated on. Spinal anesthesia, where an anesthetic is injected into the spinal fluid to numb the lower half of the body, became a common technique. This was perfect for leg and abdominal surgeries. The patient remained awake, which meant they could breathe on their own, and their cardiovascular system was more stable. This reduced the risks associated with general anesthesia, especially for patients who were already in shock from their injuries. Specialists like Robert Hinkson pioneered continuous caudal anesthesia, a technique originally for childbirth, for use in military surgery, allowing for prolonged pain relief. The role of the nurse anesthetist was also solidified during this time. There simply weren't enough physician anesthesiologists to meet the demand. Nurses were given specialized training and became experts at administering anesthesia in the field. They became an indispensable part of the surgical team. Organizations like the American Association of Nurse Anesthetists worked with the military to establish training programs and standards of care. Their skill and dedication proved that highly trained nurses could safely and effectively manage anesthesia, a legacy that continues in hospitals all over the world today. The war forced a practical approach. It stripped away the non-essentials and focused on what worked reliably under pressure. The simple, rugged anesthetic machines developed for military use, like the Oxford vaporizer, which could deliver a stable concentration of ether without electricity, influenced post-war equipment design for years. But what fundamental mysteries of consciousness do we still not understand when we give anesthesia? How exactly do these drugs turn off awareness, and how can we be absolutely certain it's gone? Could we develop an anesthetic that selectively blocks pain and memory, but leaves a patient conscious and calm enough to cooperate during surgery? And in the future, could we use focused ultrasound or electrical fields to induce anesthesia in a specific part of the body without using any drugs at all. It's number 11, what happens when the mind becomes a casualty. For most of history, the psychological wounds of war were not seen as medical issues. They were seen as moral failings. A soldier who broke down under the stress of combat was labeled a coward. The condition was called shell shock in the First World War, a term that suggested a physical brain injury from the blast of an explosion. But doctors were starting to realize that the problem was much deeper. You didn't have to be near a shell to be affected. The constant fear, the exhaustion, the horror of what was happening, and these things could break a mind just as surely as a piece of shrapnel could break a bone. During World War II, the scale of this problem became impossible to ignore. The military was discharging thousands of soldiers for psychiatric reasons. It was a massive loss of manpower, and they needed a solution. This was the moment when psychiatry was forced out of the asylum and onto the front lines. The military began to understand that mental health was a critical component of a soldier's fitness. A new term came into use, combat fatigue or battle exhaustion. This change in language was important. It medicalized the condition. It suggested something that was a reaction to an extreme situation, not an inherent weakness in the person. Military leaders like General George S. Patton were initially resistant to this idea, but the overwhelming number of cases forced a change in policy. Psychiatrists were brought into the military in large numbers for the first time. Two of the most influential were William Menninger and John Appel. They argued for a new approach based on a few simple principles, which they called PI: proximity, immediacy, and expectancy. Immediacy meant treating the soldier as soon as symptoms appeared. Don't wait for a complete breakdown. Proximity meant treating them as close to their unit and the front lines as possible. Sending a soldier all the way back to a hospital in the United States often made things worse. It solidified the idea that they were sick and made it much harder for them to return. The new approach was to pull them out of the line for a short period, maybe 24 to 72 hours at a forward aid station. Here, they could get hot food, a clean bed, and a chance to sleep. Most importantly, they could talk to someone, a psychiatrist or a trained officer, about what they had experienced. The final principle was expectancy. These soldiers were explicitly told that they were having a normal reaction to an abnormal situation. They were told that they were expected to rest, recover, and return to their unit. This was a powerful message. It removed the shame and stigma and framed recovery as a duty. This forward treatment model was remarkably successful. Reports from the U.S. Army in Europe showed that a majority of soldiers treated with these principles were able to return to combat duty. It was a pragmatic solution to a military problem, but it had profound implications for our understanding of trauma. It was the first large-scale recognition of what we now call post-traumatic stress disorder, PTSD. The psychiatrists of the war were meticulously documenting the symptoms: nightmares, flashbacks, hypervigilance, emotional numbness, and sudden outbursts of anger. Their clinical descriptions, published in medical journals after the war, laid the groundwork for the formal diagnosis of PTSD that would come decades later. The war also forced a change in how soldiers were selected. Psychiatrists developed screening tools to try to identify recruits who might be more susceptible to psychological breakdown. While these early tools were crude, it was the beginning of psychological screening for high-stress jobs, something that is now standard practice in the military, police forces, and other fields. The sheer number of psychological casualties also led to a massive need for mental health professionals after the war. This spurred the growth of clinical psychology and psychiatry in the United States. The Veterans Administration became the single largest employer of psychologists in the country, and the National Institute of Mental Health was created in 1949, in part to address the ongoing mental health needs of returning veterans. The war made it clear that the mind is as vulnerable as the body, and that the wounds it sustains are just as real. Why do some people experience extreme trauma and seem to recover fully, while others develop debilitating, long-term PTSD? What is happening in the brain at a neurological and chemical level during a traumatic event? And could we one day develop a vaccine for trauma, a psychological or pharmacological intervention that could be given to people before they enter a high-stress situation to make them more resilient to its effects? Number 10, how do you feed an entire nation on almost nothing? This food is a weapon. A country that cannot feed its people cannot sustain a long-term conflict. During the Second World War, supply lines were disrupted across the globe. Their islands were cut off, ships carrying food were sunk, farmland was turned into battlefields for nations like Britain, which imported a huge percentage of its food. This was an existential crisis. The government had to figure out how to feed tens of millions of people using only their own resources and whatever they could safely import. This challenge led to one of the largest and most detailed human nutrition experiments ever conducted. It was a science-driven approach to public health that changed our understanding of what the human body needs to survive and thrive. The British government implemented a strict system of rationing in 1940. Every man, woman, and child was issued a ration book with coupons for essential foods like meat, sugar, butter, and cheese. The goal was not just to distribute food fairly, but to make sure that the limited food available was used in the most nutritionally effective way possible. To do this, they needed data. They needed to know the absolute minimum amount of protein, fats, carbohydrates, vitamins, and minerals a person needed to stay healthy and productive. Two scientists at Cambridge University, Dr. Elsie Widdowson and Professor Robert McCants, were central to this effort. They had been studying nutrition for years, and the war gave their work a new and desperate urgency. Widdowson and McCants conducted a series of radical self-experiments. In one famous study, they put themselves and several volunteers on a diet that mimicked the expected wartime rations. It was a diet heavy on bread, potatoes, and vegetables with very little meat or dairy. They wanted to see if people could perform hard physical labor on this, restricted intake. For months, they ate this Spartan diet while undergoing a grueling regimen of cycling and hiking. They meticulously measured their own physical performance and health. The results, published in a 1942 paper in The Lancet, were astonishing. They found that they could maintain their health and fitness on this diet. They proved that bread, especially wholemeal bread fortified with calcium, could be the foundation of a healthy diet, replacing the calories lost from fat and sugar. Their research directly influenced government policy. The national loaf, a wholemeal bread, became a staple of the British diet, and its consumption was encouraged. This was public health on a massive scale. The government's Ministry of Food launched huge propaganda campaigns with slogans like "Dig for Victory," encouraging people to turn their gardens and parks into vegetable patches. They educated the public on how to cook with the foods that were available. They promoted potatoes and other vegetables as sources of essential vitamins like vitamin C. The results of this national experiment were surprising. Despite the shortages and the stress of war, the health of the British public actually improved in some ways. Infant mortality rates declined. The average height of children increased. This was because, for the first time, the poorest segments of the population were getting a diet that, while monotonous, was nutritionally balanced. They were getting less fat and sugar and more vitamins and fiber than before the war. The government was essentially enforcing a healthy diet on the entire country. This period was also a golden age for vitamin research. The importance of vitamins like A, C, and D was well understood, and the government made sure that vulnerable populations like pregnant women and young children received supplements. Orange juice and cod liver oil were distributed at clinics. This focus on micronutrients prevented the kinds of deficiency diseases that had plagued populations in previous wars. The vast amount of data collected on the British population's diet and health was analyzed for years after the war. It formed the basis of the first recommended daily allowances RDAs for various nutrients. The work of Widdowson and McCants and others like them laid the foundation for modern dietetics and proved that a scientific approach to national nutrition could have a profound impact on public health. But even with all our knowledge, why is there still so much confusion and disagreement about what constitutes a healthy diet? How much of our nutritional needs are determined by our individual genetics, and can we ever create a truly personalized diet plan? And in a world that can produce more than enough food to feed everyone, why do we still struggle with the dual problems of obesity in some regions and starvation in others? Number 9, what are the limits of a human in the sky? and humans are not meant to fly. Our bodies are designed for life on the ground at a constant gravity and with a thick oxygen-rich atmosphere. The rapid development of aviation during the Second World War pushed pilots into environments their bodies were not prepared for. They were flying higher, faster, and for longer than ever before. This created a host of new and dangerous medical problems. A pilot who lost consciousness for just a few seconds could lose their plane and their life. The field of aviation medicine emerged to understand and solve these problems, essentially figuring out how to keep a human being functional inside a high-performance machine. One of the biggest challenges was oxygen. As an airplane climbs, the air gets thinner. There are fewer oxygen molecules in each breath. Above about 10,000 feet, this leads to hypoxia or oxygen starvation. The symptoms are insidious. At first, a pilot might feel euphoric, almost drunk. Their judgment becomes impaired. Their vision narrows. Eventually, they lose consciousness. To study this, medical researchers used decompression chambers on the ground. These were sealed rooms where they could pump out the air to simulate the conditions at high altitude. Or volunteers, often the researchers themselves, would sit in these chambers and perform tasks while the altitude was increased. They meticulously documented the effects of hypoxia on the human body. One of the pioneers in this area was Harry G. Armstrong, who founded the U.S. Air Force School of Aviation Medicine. His 1939 book, Principles and Practice of Aviation Medicine, became the Bible of the field. This research led directly to the development of better oxygen masks and delivery systems that became standard equipment for all air crews. Another major problem was G-forces. When a plane pulls out of a steep dive or makes a tight turn, the pilot is subjected to powerful acceleration forces, or Gs. Positive G-forces pull the blood from the head down towards the feet. This causes the vision to gray out, then narrow into tunnel vision, and finally results in a complete loss of consciousness, known as GLOC. To combat this, researchers developed the first anti-G suits. These were trousers with inflatable bladders around the legs and abdomen. When the plane entered a high G maneuver, the bladders would automatically inflate, squeezing the lower body. This prevented blood from pooling in the legs and helped keep it in the pilot's head, allowing them to withstand much higher G-forces without blacking out. Research was led by figures like Earl H. Wood at the Mayo Clinic, who used a human centrifuge to test different suit designs and study the physiological effects of extreme acceleration. There were other dangers too. Pilots and bomber crews had to contend with extreme cold at high altitudes, leading to research on heated flight suits and the dangers of frostbite. The constant vibration and noise of the engines caused fatigue and hearing damage. The psychological stress of combat flying was immense. Aviation medicine specialists worked on everything from designing more ergonomic cockpits to establishing proper crew rest cycles. They studied the effects of diet, caffeine, and amphetamines on pilot performance. They even worked on seemingly simple things like developing better sunglasses to protect pilots' eyes from the intense glare above the clouds. Bausch & Lomb's anti-glare sunglasses, later known as Ray-Ban aviators, were developed for this very purpose. Every aspect of the interaction between the pilot and the aircraft was put under the microscope. This was the birth of human factors engineering, the science of designing systems that work in harmony with the capabilities and limitations of the human user. The knowledge gained in aviation medicine had applications far beyond the military. The understanding of how the human body reacts to low oxygen, extreme temperatures, and G-forces was directly applicable to the challenges of spaceflight a generation later. Many of the first astronauts were test pilots who had been part of these wartime and post-war research programs. The emphasis on cockpit design and pilot safety has influenced the design of every commercial airliner flying today. The simple pre-flight checklist, a procedure designed to prevent human error, was rigorously implemented in aviation during this period and has since been adopted by other high-stakes fields, including surgery. As we look towards the future of travel, both in the air and in space, what new physiological challenges will we face? How will the human body adapt to long-duration space flights with zero gravity and high radiation? Can we genetically engineer humans to be better suited for these extreme environments? And what are the psychological effects of being isolated in a small capsule for months or years on a journey to another planet. Number 8, how do you give someone their face back? The face is our identity. It's how we present ourselves to the world and how the world recognizes us. A severe facial injury is not just a physical wound, it's an attack on a person's very being. During the war, a new type of injury became horribly common, and fighter pilots and bomber crews were flying in planes filled with fuel and oxygen. If the plane was hit, the resulting fire could cause horrific burns, especially to the face and hands, the areas not covered by their flight suits. These men, many of them in their late teens and early 20s, were left with devastating disfigurements. Conventional surgery at the time had little to offer them, but one surgeon in Britain decided to make these hopless cases his life's work. His name was Archibald McIndoe, and his work at the Queen Victoria Hospital in East Grinstead would revolutionize the field of plastic and reconstructive surgery. McIndoe was a civilian surgeon from New Zealand who was working for the Royal Air Force. He rejected the traditional piecemeal approach to burn treatment. He realized that the scar tissue that formed as a severe burn healed was the enemy. It would contract and tighten, pulling the eyelids down, sealing the mouth shut, and turning hands into useless claws. His first innovation was to abandon the use of tannic acid, the standard treatment at the time, which created a hard, crusty layer over the burn. He found this actually hindered healing and promoted infection. Instead, he pioneered the use of saline baths. Patients would be submerged in a warm salt water solution, which gently cleaned the wounds and promoted the growth of healthy tissue. His most important contribution was his development of new skin grafting techniques. The challenge with facial burns was that you needed to cover large, complex, three-dimensional surfaces. McIndoe perfected the walking stock tubed pedicle graft. This was a radical procedure. A surgeon would create a flap of skin on the patient's chest or abdomen, but instead of cutting it off completely, they would leave one end attached to its original blood supply. They would then roll the flap into a tube or pedicle and sew the other end near the area that needed repair, like the wrist. After a few weeks, a new blood supply would grow into the attached end. The surgeon could then detach the original end from the chest and walk it up the body, attaching it closer to the face. This process might be repeated several times over many months, with the tube of living skin acting as its own pipeline for blood. Finally, the tube would be opened up and used to reconstruct a nose, an eyelid, or a lip. It was a slow, painful process that required dozens of operations, but it allowed McIndoe to move large amounts of healthy, well-supplied skin to the face, creating results that were previously unimaginable. But McIndoe's genius was not just surgical. He understood that the psychological recovery of his patients was just as important as the physical one. He created a unique environment at the hospital. He threw out the strict military discipline. His patients, who called themselves the Guinea Pig Club because of the experimental nature of their surgeries, were allowed to wear their own clothes and drink beer in the ward. McIndoe encouraged the local townspeople of East Grinstead to accept the men, despite their shocking appearances. He told them to treat the men as normal, not to stare or show pity. The town became known as the town that did not stare. This social and psychological support was a critical part of the healing process. It helped these men regain their confidence and their will to live. The techniques developed by McIndoe and his team became the foundation of modern reconstructive surgery. The principles of moving tissue with its own blood supply are still used today in countless procedures, from breast reconstruction after cancer to reattaching severed limbs. His holistic approach, treating the emotional and social needs of the patient alongside their physical injuries, was a forerunner of the modern, patient-centered model of care. The Guinea Pig Club continued to meet for decades after the war, a testament to the incredible bond forged between the surgeon and the men whose lives and faces he rebuilt. What are the biological barriers that still prevent us from perfectly regenerating skin after a severe burn? Will we ever be able to grow a complete custom-made face in a lab for transplantation? And as cosmetic surgery becomes more advanced, what is the line between reconstruction and enhancement, and who gets to decide what a normal face should look like? Number 7, how do you stop an invisible enemy before it spreads? War is not just fought between armies. It's also fought against disease. Throughout history, more soldiers have died from infections like dysentery, typhus, and influenza than from combat. A military base with thousands of people living in close quarters, often with poor sanitation, is the perfect breeding ground for an epidemic. An outbreak could cripple an army faster than any enemy attack. During the Second World War, public health officials understood this threat. In the United States, a huge number of new military bases and industrial centers were being built, particularly in the southern states. This brought large populations into areas where mosquito-borne diseases, especially malaria, were a serious problem. The government needed a way to protect both the soldiers and the civilian workers, who were crucial to the war effort. In 1942, a new agency was created within the U.S. Public Health Service. It was called the Malaria Control in War Areas, or MACWA. Its mission was simple: to control malaria and other infectious diseases in and around military facilities. This was a massive public health undertaking. The director of the MACWA, Dr. Louis Llewellyn Williams Jr., was an expert in malaria control. The agency's headquarters were established in Atlanta, Georgia, in the heart of the malaria belt. The MACWA was staffed with a unique mix of experts, doctors, engineers, and entomologists, scientists who study insects. This interdisciplinary approach was key to its success. The engineers worked on source reduction. They drained swamps and cleared ditches to eliminate the stagnant water where mosquitoes lay their eggs. This was a brute force, but highly effective method. The entomologists worked on a more targeted approach. They would go out into the field and study the habits of the Anopheles mosquito, the species that carries malaria. They figured out where they bred, when they bit, and how far they flew. This allowed them to focus their control efforts on the most critical areas. They also pioneered the large-scale use of a new chemical weapon in the fight against insects, DDT. In the 1940s, DDT was seen as a miracle chemical. It was incredibly effective at killing mosquitoes. MACWA teams would spray the inside walls of houses and barracks with DDT. When a mosquito landed on the wall, it would die. This technique, called indoor residual spraying, dramatically reduced malaria transmission rates. The MACWA's work was not limited to malaria. They tackled a wide range of public health problems. They worked to improve sanitation at military bases, ensuring clean water and safe disposal of sewage to prevent diseases like typhoid and dysentery. They also played a key role in controlling typhus, a deadly disease spread by lice. The development of an effective typhus vaccine and the use of DDT to kill lice were crucial in preventing major outbreaks among troops. The agency was a model of applied science. It took the latest research from the lab and deployed it on a massive scale in the field. It was data-driven, meticulously tracking disease rates and mosquito populations to measure the effectiveness of its interventions. The MACWA was so successful that after the war, public health leaders realized that its mission should be expanded. The fight against infectious diseases was not over. In 1946, the agency was reorganized and renamed the Communicable Disease Center, or CDC. Its mission was broadened to tackle any infectious disease that was a threat to the nation. From its modest beginnings as a malaria control program, the CDC has grown into one of the world's leading public health institutions. It is the organization that tracks flu outbreaks, investigates foodborne illnesses, and leads the fight against global pandemics. Its origins as a rapid response agency born out of the necessities of war are still visible in its culture today. The CDC's ability to quickly deploy teams of experts, its disease detectives anywhere in the world, can be traced directly back to the work of those MACWA teams who battled mosquitoes in the swamps of the American South. As new and unknown viruses continue to emerge, can we ever get ahead of the next pandemic, or are we always destined to be one step behind? How do we balance the need for public health interventions with individual liberties and privacy? And in an age of global travel, is it even possible to contain a highly infectious disease within one country's borders? Number 6, what if a mosquito was more dangerous than a bullet? In the European theater of the war, armies fought over cities and farmland. In the Pacific, they fought in jungles and on remote islands where the deadliest enemy was often microscopic. It was a parasite called Plasmodium, the organism that causes malaria. It was transmitted by the bite of an infected mosquito, and it was everywhere. Malaria could put a soldier out of action for weeks, with recurring cycles of high fever, bone-rattling chills, and debilitating weakness. At its worst, it could be fatal. In some campaigns, the number of casualties from malaria was far higher than the number of combat casualties. Controlling this disease was not just a medical issue, it was a strategic imperative. For centuries, the only effective treatment for malaria was quinine, a substance derived from the bark of the cinchona tree. The problem was that at the start of the war, most of the world's cinchona plantations were in Java, an island in the Dutch East Indies. When this area was occupied by Japanese forces in 1942, the Allied powers were cut off from their primary supply of quinine. This created a crisis. They desperately needed a new anti-malarial drug, and they needed it fast. The US government launched a massive coordinated research program to find a synthetic substitute for quinine. It involved thousands of scientists at universities, pharmaceutical companies, and government laboratories. It was one of the most intensive medical research projects of the war, second only to the penicillin project. Scientists scoured the globe for potential cures. They tested over 14,000 different chemical compounds for their ability to fight the malaria parasite. They revisited an older German drug called atabrine quinacrin. It was effective, but it had unpleasant side effects. It turned the skin a yellowish color, leading to a false belief that it caused jaundice, and it often caused gastrointestinal problems. Despite this, it was produced in massive quantities and became the standard prophylactic drug for troops in the Pacific. Soldiers were ordered to take it daily. Adherence was a major problem, but when taken correctly, it was highly effective at suppressing the symptoms of the disease. But the real breakthrough came from the search for a new, better drug. Researchers focused on a class of compounds known as 4-aminoquinolines. A substance called chloroquine had actually been synthesized by German scientists in 1934, but it was initially dismissed as being too toxic. American researchers, as part of the national program, re-examined it. Through a series of clinical trials, many of which were conducted on volunteer prisoners and conscientious objectors, they discovered that chloroquine was not only safe at the correct dosage, but was also a far more effective and less toxic anti-malarial than either quinine or atabrine. It worked faster, had fewer side effects, and could be used for both treatment and prevention. The results of this research were kept secret until after the war. The key paper summarizing the findings, the antimalarial properties of chloroquine, was published in the Journal of the American Medical Association in 1946. A chloroquine became the wonder drug for malaria. After the war, it was a cornerstone of the global malaria eradication campaigns of the 1950s and 60s. It saved millions of lives and allowed many tropical countries to thrive. The wartime research program also led to the discovery of another important anti-malarial drug, primaquine. Scientists found that some forms of the malaria parasite could lie dormant in the liver for years, causing relapses long after a person had left a malarial zone. They discovered that primaquine was uniquely effective at killing these dormant liver stage parasites, providing a radical cure. The coordinated, government-funded, multi-institution approach to drug discovery that was pioneered during the war became a model for future public health research, particularly in the area of tropical diseases. Why has the malaria parasite been so successful at developing resistance to nearly every drug we've thrown at it, including chloroquine? Will we ever be able to develop a truly effective and long-lasting vaccine against such a complex parasite? And given that the mosquito is the vector for so many diseases, would it be ethical to use genetic engineering to drive the entire species to extinction? And what would be the unintended consequences for the ecosystem? Number 5, could a washing machine part save your life? The kidneys are a quiet miracle. They work 24 hours a day, filtering your blood, removing waste products, and balancing the levels of water and salt in your body. When they fail, it's a death sentence. Toxins build up in the blood, a condition called uremia, and the body slowly poisons itself. Before the 1940s, there was no treatment for kidney failure. It was a fatal condition. But during the German occupation of the Netherlands, a young Dutch physician named Willem Kolff refused to accept this. Working in a small provincial hospital with limited resources, he was determined to build a machine that could do the work of a failing kidney. He wanted to build an artificial kidney. The idea of filtering blood outside the body was not entirely new, but no one had ever built a practical working device. Kolff was a brilliant and resourceful innovator. He knew the basic principle he needed to use dialysis. This is the process where small waste molecules in the blood pass through a semi-permeable membrane into a cleaning solution called a dialysate, while larger, important molecules like proteins and blood cells are left behind. The challenge was finding the right materials and building the machine. In Nazi-occupied Holland, this was almost impossible. He had to scavenge for parts. His first artificial kidney, built in 1943, was a marvel of improvisation. The centerpiece was a 40-meter-long tube of cellophane sausage casing. He knew that cellophane was a semi-permeable membrane. He wrapped this tubing around a large wooden drum that was mounted horizontally in a 100-liter tank of dialysate solution. The drum itself was made from aluminum slats from a downed bomber plane. An electric motor, taken from a Ford water pump, would rotate the drum, moving the cellophane tubing through the bath. Blood would be drawn from an artery in the patient's arm, pumped through the cellophane tubing, where the dialysis would occur, and then returned to a vein. It was a crude, clunky machine, but the principle was sound. Kolff's first 15 patients all died. The machine could remove toxins from their blood, but they were too sick by the time they received the treatment. Their conditions were irreversible. It was a heartbreaking series of failures. Many people would have given up, but Kolff persisted. In 1945, he treated his 16th patient, a 67-year-old woman who was in a uremic coma. She was dying of acute kidney failure. He hooked her up to his machine. Over 11 hours, the machine slowly cleaned her blood. Her condition began to improve. She woke up from the coma. Her own kidneys, given a chance to rest and heal while the machine did their work, began to function again. She lived for another 7 years. It was the first time in history that a person's life had been saved by an artificial kidney. It was a monumental breakthrough. After the war, Kolff shared his designs freely. He wanted the technology to spread. He sent his machines to hospitals in London, Montreal, and New York. He moved to the United States and continued his pioneering work at the Cleveland Clinic and later at the University of Utah. His original rotating drum kidney was improved upon by other researchers, leading to the more efficient dialyzers that are used today. His invention opened the door to a new era of medicine. It meant that acute kidney failure was no longer a death sentence. It also laid the groundwork for chronic dialysis, the procedure that allows people with permanent kidney failure to live for decades. Kolff is rightfully known as the father of artificial organs. His work on the artificial kidney led him to later develop the first artificial heart that was successfully implanted in a human. His story is a powerful example of how a single, determined individual working under the most difficult circumstances can change the world. Why do some people's kidneys fail while others remain healthy into old age? Can we ever learn how to trigger the human body's own regenerative processes to heal or regrow a damaged kidney, making dialysis obsolete? And if we can build an artificial kidney and an artificial heart, what is the theoretical limit? Could we one day build a complete artificial human body? Number 4, how do you put life itself in a bottle? In blood is the river of life. When it's lost, life ebbs away with it. On the battlefield, the most common cause of death is not the initial injury itself, but the resulting blood loss and shock. For years, doctors knew that replacing lost blood through transfusion could save lives. But there was a huge logistical problem. Well, blood is a living tissue. It's fragile and perishable. It requires careful typing and cross-matching to prevent a fatal reaction. It needs to be refrigerated. How could you possibly create a system to collect blood from donors, test it, store it, and transport it thousands of miles to a field hospital in time to save a soldier's life? This was the challenge that led to the development of modern blood banking. One of the first major hurdles was storage. In the 1930s, blood could only be stored for a few days before it went bad. A major breakthrough came when researchers discovered that adding a citrate dextrose solution to the blood could extend its shelf life to several weeks. This made the idea of a blood bank, a place where blood could be stored and then withdrawn when needed, a practical possibility. But the real game changer was the discovery that you didn't always need to transfuse whole blood. For many trauma patients, the most critical need is to replace the lost fluid volume to treat shock. The liquid component of blood, the plasma, could do this just as well as whole blood. Plasma had two huge advantages. First, type AB plasma can be given to anyone regardless of their blood type, making it a universal fluid expander. This eliminated the need for time-consuming cross-matching in an emergency. Second, and most importantly, plasma could be dried. Through a process called lyophilization or freeze-drying, all the water could be removed from the plasma, turning it into a stable powder. This dried plasma could be stored for months at room temperature in a sealed container. When it was needed, a medic could simply add a container of sterile water, shake it, and have a life-saving intravenous fluid ready in minutes. It was a medical miracle, life in a bottle. The effort to create a large-scale plasma program was immense. In the United States, the Plasma for Britain project started in 1940, before the U.S. even entered the war, was one of the first major initiatives. It was spearheaded by an African-American surgeon named Dr. Charles R. Drew. Drew was a brilliant researcher who had done his doctoral work at Columbia University on the topic of banked blood. He developed a systematic factory-like process for collecting and processing large quantities of plasma. His methods for ensuring the plasma was sterile and safe were a major contribution. He was appointed the medical director of the American Red Cross's first blood bank, which was tasked with providing blood and plasma for the U.S. military. His organizational genius created the model for the national blood donation system we have today. Tragically, Drew's work was marred by the policy of racial segregation. The military initially demanded that the blood of white and black donors be stored separately. Drew, knowing there was no scientific basis for this, protested vigorously. He argued that it was unscientific and insulting, though he was eventually forced to resign his position over this issue. His pioneering work had already established a system that would save hundreds of thousands of lives. The Blood for Britain and later national campaigns mobilized millions of ordinary citizens to donate blood, creating a sense of shared purpose on the home front. The iconic images of nurses and Red Cross volunteers collecting blood became a symbol of the war effort. The ability to give plasma right at the front lines, administered by a combat medic, was a key factor in the dramatic increase in survival rates for wounded soldiers. The legacy of these wartime blood programs is all around us. The modern, volunteer-based blood donation system, run by organizations like the Red Cross, is a direct descendant of these efforts. The science of blood component therapy, separating blood into its different parts, like red cells, platelets, and plasma, so that a patient can be given only the part they need, was developed out of this research. The techniques for plasma fractionation, the process of extracting specific proteins like albumin from plasma, were also perfected during this time. Every time someone receives a blood transfusion in a hospital, they are benefiting from the systems and science born out of this urgent need. What are the risks we still don't understand about blood transfusion? Are there subtle, long-term immunological consequences of receiving another person's blood? Could we ever create a truly universal artificial blood substitute that carries oxygen and has no risk of disease transmission? And if we could, what would that mean for the altruistic system of volunteer blood donation? Number 3, can you stop a pandemic during a war? In 1918, a new strain of influenza swept across the globe. It was one of the deadliest pandemics in human history, killing far more people than the First World War itself. The memory of this catastrophe was fresh in the minds of military and public health officials as a new global conflict began in the 1930s and 40s. They knew that a similar pandemic striking crowded military camps and dense urban centers could be devastating. They needed a weapon to fight the flu virus. They needed a vaccine. Developing a vaccine against the flu is incredibly difficult. Unlike diseases like measles or polio, which are caused by stable viruses, the influenza virus is constantly changing. It mutates from year to year, which is why we need a new flu shot every season. In the 1930s, scientists were just beginning to understand this. In 1933, researchers in England first isolated the human influenza A virus. This was the critical first step. You can't make a vaccine until you know what you're fighting. A few years later, an Australian virologist named Frank McFarlane Burnett made another key discovery. he found that the flu virus could be grown in fertilized chicken eggs. This was the breakthrough that made large-scale vaccine production possible. The nutrient-rich environment of the egg was a perfect incubator for the virus. As the war began, the U.S. military, fearing a repeat of 1918, put a high priority on developing a flu vaccine. A commission was formed to coordinate the efforts of researchers across the country. One of the leading figures in this effort was a virologist named Dr. Thomas Francis Jr. at the University of Michigan. Francis and his team, which included a young researcher named Jonas Salk, who would later become famous for developing the polio vaccine, worked to create a killed virus vaccine. The idea was to grow large quantities of the virus in eggs, harvest it, and then kill it with a chemical like formaldehyde. The dead virus could no longer cause infection, but the proteins on its surface could still trigger the body to produce a protective immune response. By 1943, they had a promising vaccine. The military decided to conduct the first large-scale, controlled field trial of a flu vaccine. It was a massive undertaking involving multiple universities and thousands of Army personnel who were part of a specialized training program. The results of the study, published in the American Journal of Hygiene in 1944, were a resounding success. The vaccine was shown to be safe and about 75% effective at preventing the flu. This was proof that a killed virus vaccine could work. Based on these results, the U.S. Army decided to vaccinate all of its personnel in late 1945. The vaccine was produced by several pharmaceutical companies using the egg-based method pioneered by Burnett and refined by Francis's group. This was the first time an inactivated viral vaccine had been produced and used on such a massive scale. The program was a huge logistical and scientific achievement. It proved the feasibility of mass vaccination campaigns against respiratory viruses. The basic technology, growing the virus in eggs, inactivating it, and purifying it, remained the standard method for producing flu vaccines for more than 50 years. The work of Francis Salk and the Military Commission established the scientific framework for our modern annual flu vaccination program. It also helped to establish the model of government, academia, and industry collaborating to solve a major public health crisis, a model that has been used time and again, most recently in the rapid development of vaccines for COVID-19. The wartime flu vaccine program may not be as famous as the penicillin project, but it was a landmark achievement in preventive medicine. Why does the flu vaccine's effectiveness vary so much from year to year? Are we getting any closer to creating a universal flu vaccine that would protect against all strains and last for many years? And what other viruses currently circulating harmlessly in animal populations have the potential to jump to humans and cause the next global pandemic? Number 2, could a poison be turned into a cure? It started with a weapon, a truly awful one. Nitrogen mustard is a chemical agent that causes severe blisters on the skin and in the lungs. During the war, governments were terrified that this type of chemical weapon would be used, so they launched secret research programs to understand its effects and hopefully to find an antidote. As part of this research, 2 pharmacologists at the Yale School of Medicine, Louis S. Goodman and Alfred Gilman, were tasked with studying the systemic effects of nitrogen mustard. They were looking for a way to protect soldiers from its deadly power. But in the course of their work, they noticed something strange. When they administered the chemical to laboratory animals, they saw that it had a profound and destructive effect on the blood. Specifically, it rapidly destroyed white blood cells, particularly the lymphocytes and other cells of the lymphatic system. This was a catastrophic effect for a healthy person, but Goodman and Gilman had a flash of insight. They knew of diseases where the body produces too many of these cells, diseases like lymphoma and leukemia. These are cancers of the blood and lymphatic system. Their thought was radical, almost unthinkable. What if this poison, this destructive chemical agent, could be used as a targeted therapy? What if you could use it to destroy the cancerous cells that were overwhelming a patient's body? It was a dangerous idea. They were proposing to inject a known poison into a human being. They sought the collaboration of a surgeon at Yale, Gustav Linskog. In December of 1942, they had a patient. He was a man in his late 40s, known in the medical records only by his initials, JD. He had advanced lymphosarcoma. Tumors had invaded his lymph nodes, face, and neck. He was in terrible pain, could barely breathe or swallow, and had failed all conventional treatments, which at the time consisted only of radiation therapy. He was dying. With his consent, they began the treatment. Over several days, they gave him small, carefully calculated intravenous injections of nitrogen mustard. The entire experiment was conducted in secret. The results were astonishing. Within days, the tumors began to soften and shrink. The patient's pain subsided. He could swallow again. He could sleep. The masses of cancerous tissue that had been choking him were melting away. The effect was temporary. The cancer eventually came back, and JD died a few months later. But for a brief period, the treatment had worked. It was a proof of concept. It demonstrated for the very first time that a drug could be used to effectively treat a systemic cancer. This was the birth of chemotherapy. Because of the secrecy surrounding chemical weapons research, the results of this groundbreaking experiment were not published until after the war. In 1946, Goodman, Gilman, and their colleagues published their findings in a paper in the Journal of the American Medical Association. The news was a bombshell in the medical community. It opened up an entirely new field of cancer treatment. Other researchers began to build on their work. In Boston, a pathologist named Sidney Farber, inspired by the nitrogen mustard story, began to experiment with other chemicals that could interfere with cell growth. In 1947, he used a drug called aminopterin to induce the first temporary remissions in children with acute lymphoblastic leukemia, which until then had been a uniformly and rapidly fatal disease. This was the beginning of combination chemotherapy, the use of multiple drugs to attack cancer from different angles. The legacy of that secret experiment in 1942 is profound. Nitrogen mustard itself and its derivatives like cyclophosphamide are still used to treat certain cancers today. But more importantly, the principle that Goodman and Gilman established and that cancer could be fought with chemicals is the basis of one of the three main pillars of modern cancer therapy, alongside surgery and radiation. It was a turning point, a moment when a weapon of war was transformed into a tool of healing, all because two scientists were observant enough to see a potential cure in the destructive effects of a poison. Why do some cancers respond dramatically to chemotherapy only to develop resistance and come back even more aggressively? Can we ever design a chemotherapy drug that is so perfectly targeted that it kills every last cancer cell in the body while leaving every single healthy cell completely unharmed? And what other substances in our environment, natural or man-made, that we currently consider to be dangerous poisons, might be hiding a similar therapeutic potential? Number one, what if a speck of mold could change everything? Before the 1940s, a simple scratch could kill you. A cut from a kitchen knife, a fall in the schoolyard, a surgical incision, any of these could lead to a bacterial infection that would overwhelm the body's defenses. Diseases like pneumonia, meningitis, and sepsis were often death sentences. Doctors had very few tools to fight these infections. They could promote hygiene and they could offer supportive care, but they had no weapon that could kill bacteria inside the human body. The world was waiting for a miracle, and that miracle came from a speck of mold. The story began in 1928 with a famously messy scientist named Alexander Fleming. At his lab in London, he noticed that one of his petri dishes, which had been contaminated with a blue-green mold called Penicillium notatum, had a strange clear zone around the mold. The bacteria he had been trying to grow on the dish would not grow near the mold. He correctly deduced that the mold was producing a substance that was killing the bacteria. He called this substance penicillin. Fleming published his findings, but he was unable to isolate and purify the active ingredient. The mold juice was unstable and difficult to produce in large quantities. For a decade, his discovery remained a scientific curiosity, a footnote in medical journals. The Second World War changed everything. The prospect of millions of soldiers suffering from infected wounds created an urgent need for an effective antibacterial agent. A team of scientists at Oxford University, led by Howard Florey and Ernst Boris Chain, decided to revisit Fleming's work. They were a brilliant and diverse team. Florey was a determined pathologist, Chain was a gifted biochemist, and another key member, Norman Heatley, was an expert in designing laboratory equipment. Starting in 1939, they embarked on the painstaking work of figuring out how to purify penicillin. It was a monumental task. They had to grow the mold in thousands of containers, from bedpans to biscuit tins. Heatley designed a clever apparatus that could extract the tiny amounts of active penicillin from huge volumes of the mold culture fluid. By 1940, they had produced enough purified penicillin to test on mice. In a landmark experiment, they infected 8 mice with a lethal dose of Streptococcus bacteria. They treated 4 of the mice with penicillin. The next morning, the 4 untreated mice were dead. The 4 that had received penicillin were perfectly healthy. It worked. The first human patient was a police constable named Albert Alexander, who in 1941 was dying from a massive infection that had spread from a scratch on his face. The Oxford team gave him their entire supply of penicillin. He made a miraculous recovery, but then their supply ran out. They couldn't make it fast enough. The infection returned, and he died. It was a tragic lesson. They needed to be able to produce penicillin on an industrial scale. Britain, under constant attack, did not have the resources for such a massive undertaking. In the summer of 1941, Florey and Heatley traveled to the United States to plead for help. They were put in touch with researchers at the U.S. Department of Agriculture's lab in Peoria, Illinois. This was a turning point. The Peoria lab specialized in fermentation, and they made 2 crucial contributions. First, a lab assistant found a new, more potent strain of penicillium on a moldy cantaloupe she found at a local market. This strain, along with subsequent mutations induced by radiation, would produce hundreds of times more penicillin than Fleming's original. Second, the researchers discovered that by adding corn steep liquor, a waste product of the corn processing industry, to the growth medium, they could increase the yield even further. With these breakthroughs, the American government and a consortium of pharmaceutical companies, including Pfizer and Merck, launched an all-out effort to mass-produce penicillin. They had to invent entirely new technologies for deep tank fermentation to grow the mold in huge 20,000-gallon vats. It was an engineering challenge on a par with the most complex weapons programs. By 1944, they were producing enough penicillin to treat all of the Allied forces. The impact was immediate and profound. Soldiers who would have died from infected wounds, from pneumonia, or from gas gangrene were now surviving. The drug was so precious that in some field hospitals, they would collect the urine of patients who had been treated with penicillin to extract and reuse the drug that hadn't been metabolized. The discovery and mass production of penicillin was one of the greatest medical achievements of the 20th century. It ushered in the age of antibiotics and fundamentally changed the relationship between humanity and infectious disease. How do bacteria so quickly develop resistance to the antibiotics we create? And are we losing the evolutionary arms race against them? Could there be thousands of other life-saving antibiotics waiting to be discovered in other molds, fungi, and soil bacteria that we have not yet studied? And what will happen if we reach a post-antibiotic era where our current drugs no longer work and a simple infection becomes once again a deadly threat?